There is a moment, if you watch the footage carefully, when the robot stops looking like a machine trying to walk and starts looking like something else entirely. It was the fall of 2022 when Elon Musk stepped onto a stage in Palo Alto and introduced the world to Optimus. The presentation was, by Silicon Valley standards, modest. A prototype shuffled out under bright lights, raised one hand in a slow wave, and the crowd responded with something between applause and nervous laughter. The thing moved like a person recovering from a long illness, cautious, deliberate, every step a small negotiation with gravity. Musk, never one to undersell a moment, told the audience that this robot would one day be more valuable than every car Tesla had ever built. Most people in that room probably did not believe him. That skepticism was entirely reasonable. The history of humanoid robotics is long and largely made of broken promises. For decades, researchers and entrepreneurs have been announcing the imminent arrival of machines that walk, talk, and work alongside people. Honda's Osimo could climb stairs and kick a soccer ball. Boston Dynamics built robots that could backflip with unnerving grace. Dozens of startups have burned through billions of dollars, chasing a version of the future that always seemed to be about 10 years away. The graveyard of robotics companies that promised revolution and delivered disappointment is crowded and well populated. So when Musk unveiled Optimus, the reaction from serious engineers and economists was predictable. They had seen this before. They had the scars to prove it. The machine was impressive as a demonstration, they said, but demonstrations are easy. Factories are hard. The real world is messy and unpredictable, full of variables that break elegant systems in ugly ways. A robot that can wave at a crowd in a controlled environment is a very different thing from a robot that can sort components on a production line for 12 hours straight without failing. And then 2024 arrived, and something shifted. By the middle of that year, Tesla had Optimus units moving through its Fremont facility. Not performing, not demonstrating, working. They were handling battery cells, sorting parts, completing tasks that required a degree of dexterity and spatial reasoning that earlier generations of industrial robots simply could not manage. The footage that leaked out was unpolished and grainy, the kind of video you watch on a small screen while waiting for something else. But if you knew what you were looking at, it was remarkable. These were not robotic arms bolted to the floor. These were machines walking through shared human spaces, adapting to the environment around them, doing something that looked uncomfortably close to labor. This is where the story gets genuinely interesting and genuinely complicated. Automation is not new. The fear of automation is not new. Every major wave of technological change in the last 2 centuries has arrived with a chorus of voices warning that machines were about to take the jobs, hollow out the workforce, leave millions of people without purpose or income. The spinning jenny, the steam loom, the assembly line, the spreadsheet, the ATM, each one triggered a version of the same panic, and each time the economist who studied the long run pointed out that the panic was overblown. New technologies destroyed some jobs, yes, but they also created new industries, new roles, new categories of work that nobody had imagined before. The labor market was resilient. It adapted. People adapted. That argument is not wrong, but it may be incomplete. Because the question worth asking right now is not whether automation has disrupted economies before. It has. The question is whether this particular wave, the one rolling in right now, is different in kind rather than just in degree. There are a few reasons to think it might be. Previous automation was largely narrow. It targeted specific, repetitive physical tasks. Robots could weld the same seam 10,000 times. They could spray paint with perfect consistency. They could move a pallet from point A to point B on a fixed route. What they could not do was generalize. They could not look at an unfamiliar object, reason about how to handle it, and then handle it. They could not navigate a space that had changed since the last time they moved through it. They could not do the 1,000 small acts of improvisation and judgment that human workers perform constantly without even noticing. The combination of advanced machine learning and increasingly capable physical hardware is beginning to erode that boundary. Optimus is not just a mechanical body. It is a mechanical body trained on vast amounts of data. capable of something that at least resembles adaptive reasoning. When a task changes slightly, it does not freeze, it adjusts. That is a different kind of machine than anything that came before it. That is what makes the room feel different this time. There is also the question of speed. Earlier waves of automation unfolded over decades. The transition from agricultural labor to industrial labor took generations. Families had time, however painful, to adapt. Children could train for different work than their parents had done. The social systems, however imperfect, had some room to breathe. What happens when the pace of change compresses? When the gap between a technology appearing in a laboratory and appearing on a factory floor shrinks from 20 years to 5? The adaptation mechanisms that societies have relied on may not be fast enough to keep up. None of this means catastrophe is inevitable. It does not mean the economists who point to historical resilience are wrong. It means the stakes of getting this transition right are very high, and the margin for error is narrowing. It means the decisions being made right now by companies like Tesla, by policymakers, by workers and their representatives will shape the next several decades of economic life in ways that are difficult to overstate. The robot in the room is no longer a thought experiment. It is not a concept video or a press release or a prototype wheeled out under flattering lights. It is a physical presence on working factory floors, doing real tasks, learning from real environments, improving at a pace that surprises even the people building it. The conversation about what that means for workers and wages and the nature of work itself is not a conversation we can afford to keep postponing. That conversation is what this book is about, and it begins, as most honest conversations do, by acknowledging what we do not yet know. The ground is shifting. The question is whether we are paying close enough attention to keep our footing. To keep your footing, it helps to understand exactly what is moving beneath you. And in this case, what is moving is a machine that weighs about 70 kilograms, stands roughly 5'8", and is attempting to do something that took biological evolution hundreds of millions of years to figure out: walk upright, use its hands, and adapt to a world that was not built for it. That is a useful place to start, because before we can talk about what Optimus means for the economy, or for labor, or for the texture of everyday working life, we need to understand what it actually is. Not in the abstract, in the specific, physical, computational sense. What holds it up? What makes its fingers close? What happens inside its processing stack in the fraction of a second between sensing the world and responding to it? Let's begin with the body. The skeleton of a humanoid robot like Optimus is built around a series of actuators, which are the mechanical equivalents of muscles. They convert energy into movement. Early industrial robots relied almost exclusively on hydraulic actuators, which are powerful but heavy, prone to leaking, and poorly suited to the kind of precise, low-force tasks that hands demand. Tesla's engineers moved toward electric actuators, and more specifically, toward a class of devices that use integrated motor and gearbox assemblies custom designed to hit a difficult target: high torque, low weight, and enough precision to handle objects as delicate as an egg. There are 28 actuators in the Optimus design, distributed across the body to mirror the major degrees of freedom in human movement. The hips, knees, and ankles handle locomotion. The shoulders, elbows, and wrists extend the machine's reach. And then there are the hands, which are in many ways the hardest problem of all. Each hand has 11 degrees of freedom. That means 11 independently controllable axes of movement, driven by actuators small enough to fit inside a palm. Getting those actuators to work together fluidly, without lag, without overshoot, without the kind of mechanical shudder that would send a fragile object tumbling, required years of iterative design. But hardware alone is not enough. A body without sensing is a body that stumbles. This is where sensor fusion becomes essential. Optimus carries an array of sensors that feed information into its control systems continuously. There are cameras, which provide visual data about the environment and about the objects the robot is trying to manipulate. There are inertial measurement units, which track acceleration and angular velocity and tell the system how the body is oriented in space at any given moment. There are force and torque sensors embedded in the joints and fingertips, which register the pressure of contact and allow the robot to modulate its grip in real time. And there is a neural network-based perception stack that takes all of this information and attempts to build a coherent picture of the world fast enough to act on it. The challenge is not gathering data. The challenge is making sense of it quickly enough to matter. A human who reaches for a coffee cup is performing a computation of staggering complexity without knowing it. The visual system identifies the cup, estimates its position and orientation, and sends a motor command that adjusts continuously as the hand approaches. The sense of touch kicks in the moment fingers make contact, and the grip tightens or loosens in response to feedback that arrives in milliseconds. None of this feels like computation to us. It feels like reaching for a cup. But it is, in fact, one of the most sophisticated closed-loop control problems in nature. Optimus tries to replicate this with a layered control architecture. At the lowest level, there are fast feedback loops running at high frequency, handling the moment-to-moment adjustments that keep joints stable and prevent mechanical damage. Above that, a mid-level controller manages balance and locomotion, using algorithms derived from a branch of robotics called whole-body control, which treats the entire body as a unified dynamic system rather than a collection of independent limbs. And above that, a higher-level planning system decides what to do next based on goals and environmental state. The balance problem deserves particular attention because it is counterintuitive. Bipedal locomotion is inherently unstable. A human standing still is not in static equilibrium. We are constantly making tiny corrections, shifting weight, tensing muscles, responding to perturbations we are not even consciously aware of. The algorithms that govern Optimus's balance draw on decades of academic research and legged robotics, combined with Tesla's own simulation and training infrastructure. The robot learns to walk not just by being programmed with a gait pattern, but by training and simulation across millions of varied terrain conditions, developing a kind of generalized competence that transfers to the real world. This is where Tesla's background in machine learning becomes genuinely significant. The company spent years developing neural network training pipelines for autopilot, processing enormous volumes of real-world driving data to teach a system how to perceive and respond to complex, unpredictable environments. That infrastructure, those tools, those engineering habits translate directly to the problem of training a humanoid robot. The approach is called imitation learning in some contexts and reinforcement learning in others, and in practice, it often involves both. The robot observes demonstrations of a task, either from humans wearing motion capture suits or from synthetic data generated in simulation, and then refines its behavior through trial and error until it can execute the task reliably under real-world conditions. What emerges from this process is not a robot that follows a script. It is a robot that has developed something closer to a policy, a learned mapping from sensory inputs to motor outputs that generalizes across situations the robot has never seen before. That is a meaningful distinction. A scripted robot fails the moment something falls outside the script. A robot with a trained policy can handle variation, can adapt, can recover from the unexpected. It is still far less flexible than a human, but the gap is narrowing, and the rate of narrowing is accelerating. There is something almost vertiginous about looking closely at these systems. The closer you look, the more you see that what once seemed like the exclusive province of biology, the ability to move through space gracefully, to use hands with care and precision, to sense and respond and adapt, is becoming an engineering problem. A hard one, a profoundly difficult one, but a solvable one. And the people building Optimus believe they are solving it, iteration by iteration, training run by training run, in a facility in Austin where machines are learning to move the way we move, so that one day they might work the way we work. So they are solving it, and the question that follows naturally is, what happens when the solution leaves the lab and walks onto the factory floor? The Gigafactory in Fremont, California, is not a quiet place. It never has been. It is a building so large that workers used to joke you could fit multiple aircraft carriers inside it, and on any given shift, the noise is a continuous, layered wall of sound. Stamping presses, conveyor belts, pneumatic tools, the low electronic hum of thousands of battery cells moving through automated channels. Into that environment, Tesla began introducing Optimus units for supervised task work sometime in late 2024. Not as a spectacle, not as a demonstration, as labor. The tasks they started with were chosen carefully. Deliberately unglamorous, sorting and transferring battery cells from trays into specific fixtures, moving components between workstations along defined paths, picking up parts that had been placed in consistent positions and setting them down in consistent positions somewhere else. These are jobs that a human worker can learn in an afternoon. They are also jobs that require a human worker to do the same motion thousands of times across a 10-hour shift. The fatigue is real, the repetitive strain injuries are real, and the robots, in theory, feel neither. What the robots did feel, or rather, what the engineers measured, was error rate. That is the first and most fundamental metric on a factory floor. How often does a task get done correctly? For early Optimus deployments, the answer was encouraging, but not yet clean. The units performed well under stable conditions. They struggled when conditions shifted. A tray placed 2 inches off center, a part with a slightly different surface texture than the training data had anticipated. A shadow falling across a workpiece at an angle the vision system hadn't encountered before. The physical world, it turns out, is not a controlled laboratory. It never is. The second metric is cycle time. How long does it take the robot to complete 1 unit of work? And here the picture is more complicated. Optimus, in its current form, is not fast. A human worker with experience can often complete the same pick-and-place task in a fraction of the time. The robot moves with a kind of deliberate care, not hesitation exactly, but the caution of a system that is still integrating its sensory data, still confirming before it commits. The engineers are not apologetic about this. They will tell you that speed is a software problem, and software problems get solved with updates. The question they care more about is consistency. A robot that is slower but never has an off day, never rushes because the shift is ending, never puts a cell in the wrong orientation because it's tired. That robot has a different kind of value. The third metric is uptime. How many hours in a shift is the robot actually working versus paused versus waiting for a technician? This is where the human element re-enters the picture in a way that is easy to underestimate. Because Optimus units on the factory floor are not autonomous in any total sense. They operate within what the teams call a supervised deployment model. There are human workers, sometimes called robot rangiers, though the official language is more formal, whose job is to monitor the units, intervene when something goes wrong, reset the task environment when conditions drift outside acceptable parameters. These are not low-skill positions. They require understanding how the robot perceives its environment, knowing when a failure is a one-time anomaly versus a sign of a deeper calibration problem, and making judgment calls quickly in a noisy, fast-moving space. What this means in practice is that the robots and the humans are not in competition on the line. Not yet. They are in collaboration, an awkward, early-stage collaboration, but a genuine one. The human worker brings adaptability, context, the ability to look at a situation and immediately understand that something is wrong, even if they can't articulate why. The robot brings endurance, precision within its trained domain, and the ability to generate performance data that the engineering team can use to improve the next software build. They are, in a real sense, teaching each other. The Gigafactory in Austin, which Tesla calls Giga Texas, has been the more aggressive deployment site. It is newer, designed with more flexible manufacturing infrastructure, and the teams there have been running Optimus units on battery cell tasks with higher autonomy levels and larger sample sizes. The data coming out of those deployments has been used to train subsequent model versions, which means the robots working in Austin today are, in a meaningful way, smarter than the robots that worked in Austin 6 months ago. The learning loop is live. It is running continuously. And it is accelerating. There is a number that Tesla's robotics team has been focused on internally, though they have been careful about how publicly they discuss it. The number is not a speed target or an error rate. It is a cost per task figure, what it costs, fully loaded, to have Optimus complete 1 unit of work, compared to what it costs to have a human worker complete that same unit of work. Right now, that number does not favor the robot. The hardware is expensive, the supervision overhead is real, and the maintenance requirements add up. But the trajectory of the number matters as much as the number itself, and the trajectory, by all accounts, is moving in one direction. The workers on the line have a range of reactions to all of this, which is perhaps unsurprising. Some find the robots genuinely interesting. They stop to watch during transitions, ask the technicians questions, seem to approach the machines with a kind of curious respect. Others are more guarded, and their caution is not irrational. They have seen automation before. They know what it means when a company invests heavily in a technology that can do what they do. The reassurances from management are noted, and they are noted with the particular skepticism of people who have been in manufacturing long enough to know that reassurances are not contracts. What is true right now is that no human worker at a Tesla facility has been directly replaced by an Optimus unit. The deployments have been additions, not substitutions. Robots taking on tasks that were either unfilled or newly created by production line reconfigurations. Whether that remains true as the technology matures is a question that lives at the intersection of engineering and economics and labor policy, and it does not have a clean answer today. What does have a clean answer, or at least a clear one, is what the robot is doing on Tuesday afternoon in Giga, Texas. It is picking up a battery cell. It is placing it in a fixture. It is doing this again and again. And the data from every single repetition is flowing back into a system that is learning, quietly and continuously, how to do it a little better next time. That repetition, battery cell, fixture, again, is not just a factory scene. It is an argument. And the argument lands differently depending on where you are standing when you hear it. If you are an economist, you might see a productivity curve bending upward. If you are a policy analyst, you might see a retraining program that needs funding. And if you are one of the people who used to do that job, or whose parent did, or whose town was built around the idea that people would keep doing it for another generation, pause. You see something else entirely. You see a door closing, quietly, without ceremony, on a Tuesday afternoon. So let us be honest about what is happening to work. Not catastrophist, not dismissive, just honest. The displacement is real. Economic modeling from research institutions across the United States, Europe, and Asia has converged on a finding that is uncomfortable to state plainly. Somewhere between a quarter and a half of all current job tasks, not jobs, but tasks, are susceptible to automation within the next 2 decades. The range is wide because the future is uncertain, and anyone who gives you a single precise number is selling something. But the direction is not uncertain. The pressure is moving in one direction, and it is not reversing. History offers a useful frame here, though it also offers a warning about how we use that frame. When mechanical looms displaced hand weavers in England in the early 19th century, the long-run outcome was more textile jobs, not fewer. When agricultural mechanization swept through the American Midwest across the 20th century, it freed up labor that eventually flowed into manufacturing, services, and industries that did not yet exist when the tractors first arrived. The standard lesson economists draw from these episodes is that technology destroys jobs in the short run and creates them in the long run, and that, on balance, living standards rise. That lesson is true. It is also incomplete. The people who lost those jobs were not abstractions. The hand weavers of Nottingham did not live long enough to see the factories that eventually absorbed their grandchildren. The farmers who left the land for Detroit found cities that were, for a generation, genuinely better than what they had left, but those cities later hollowed out in their own turn. History's long-run optimism is real, but it is purchased at a cost that falls unevenly, and that cost is paid by specific people in specific places who do not get to wait for the long run to arrive. So which workers are most exposed right now? The research points toward a cluster of characteristics. Roles involving routine physical manipulation of objects in predictable environments, assembly, packaging, sorting, basic inspection, are highly vulnerable. Roles involving routine information processing, data entry, basic document review, certain categories of customer service are similarly at risk. What these jobs share is that they can be decomposed into steps, and steps can be encoded, and encoded tasks can be handed to machines that do not need breaks or benefits or a reason to show up in the morning. The workers in these roles are disproportionately people without 4-year degrees, disproportionately concentrated in specific geographic regions, and disproportionately older, which matters because retraining is harder at 53 than it is at 23, and the research is clear on that point, even when the policy conversation pretends otherwise. What is less clear and more interesting is what is growing on the other side of the ledger. Because new categories of work are emerging, even if they are not yet large enough to absorb everyone who needs them. Some of this is predictable. AI systems need people to train them, audit them, correct them when they go wrong. The person who reviews the outputs of a medical imaging algorithm, who catches the edge cases the model has never seen, who explains to a hospital administrator why the system flagged a particular scan, that is a job that did not exist 15 years ago and is now a real occupation with a real salary. The same logic applies across industries. Automation creates oversight roles, it creates integration roles, it creates the job of explaining the machine to the humans who have to live with its decisions. Some of what is growing is harder to categorize. There is a pattern emerging in labor markets where the work that holds its value is work that is irreducibly human, not because machines cannot approximate it, but because the approximation is not good enough, or not trusted, or simply not what people want. Presence matters. A physical therapist working with a patient recovering from a stroke is not just executing a protocol. A teacher managing a classroom of 9-year-olds is not just delivering content. A social worker navigating a family in crisis is operating in a domain where the human relationship is the intervention, not merely the delivery mechanism for it. These roles are not immune to change. Technology will reshape how they are done, but they are not simply displaceable in the way that sorting parcels is displaceable. There is also a category of work that is genuinely new in character, the work of managing complexity at the human-machine boundary. As automated systems proliferate, the seams between them, the places where a process moves from one system to another, where an exception occurs, where something unexpected requires judgment, those seams do not disappear. They multiply, and someone has to stand at those seams and make decisions. That someone is increasingly a new kind of worker, not a programmer exactly, not a manager exactly, but something in between. A person who understands enough about how the systems work to intervene when they fail, and enough about the human context to know what the right intervention looks like. None of this is cause for simple optimism. The new jobs are not automatically located where the old jobs were. They do not automatically pay what the old jobs paid. They do not automatically reward the skills that the displaced workers spent decades developing. The gap between the job that disappeared and the job that appeared is not always crossable, and pretending otherwise is a form of cruelty dressed up as encouragement. What we can say is this: the labor market is not a fixed container with a fixed number of slots. It has expanded before in response to technological change, and it is expanding now in ways that are partially visible and partially not. The expansion is real, the disruption is also real, and the distance between those two facts is where millions of actual human lives are being lived right now, without the benefit of knowing how the long run turns out. The machine picks up the battery cell. It places it in the fixture. Somewhere else, a person is learning a skill that did not have a name 5 years ago, trying to stay ahead of a transition that is not waiting for anyone to be ready. That distance between where the economy is going and where people are living right now does not stay abstract for long once you start looking at the numbers. The numbers are, depending on your vantage point, either extraordinary or alarming, sometimes both at once. When a company replaces a human worker with a robotic system, something interesting happens to its balance sheet. Labor costs fall, output often rises, productivity in the narrow accounting sense improves. The company's earnings grow, its shareholders benefit, and somewhere in that chain of events, the question of who actually captures the value of that improvement becomes one of the defining economic puzzles of our time. This is not a new puzzle. Economists have been turning it over for decades, but the scale and speed of automation in the 2020s has given it a new urgency, and the answers that used to satisfy, that new jobs would appear, that productivity gains would lift all boats, are being stress tested in real time. The boats are not all rising at the same rate. Some are rising very fast. Some are barely moving. To understand why, it helps to think about how economic output actually gets distributed. When a factory produces goods, the revenue from selling those goods has to go somewhere. Some goes to workers as wages. Some goes to the owners of capital, machines, buildings, intellectual property, as returns on investment. Some goes to governments as taxes. The ratio between those shares is not fixed. It shifts over time, and it shifts in response to technology. For most of the 20th century, the share going to workers held relatively steady across wealthy economies. It was never perfectly equal, but it was stable enough that economists treated it almost as a constant. Then, starting roughly in the 1980s and accelerating through the 2000s and 2010s, that share began to fall. Capital's share rose. And one of the leading explanations for that shift is the substitution of machines for human labor in more and more parts of the economy. Robotics and automation are not the only forces driving this. Globalization, the decline of unions, changes in corporate governance, all of these played roles. but automation is increasingly central to the story, and it is accelerating. The question is not whether the shift is happening. The question is what, if anything, we choose to do about it. That question has produced some of the most heated policy debates of the past few years. Two ideas in particular have moved from the academic margins towards something resembling mainstream conversation. The first is universal basic income. The second is a tax on robots, or more precisely, on the automation of labor. They are related ideas, and they are both responses to the same underlying anxiety that if machines do more and more of the work, and the gains flow primarily to the owners of those machines, then a growing share of the population could find themselves economically stranded. Universal basic income, the idea of giving every citizen a regular cash payment, no strings attached, has been debated in various forms for centuries, but it gained new traction in the 2010s and into the 2020s as automation anxiety intensified. Pilots were run in Finland, in Kenya, in parts of the United States. The results were genuinely interesting. Recipients did not, by and large, stop working. They tended to work differently, taking more risks, pursuing education, starting small businesses. Mental health outcomes improved. The programs were expensive, and the question of how to fund them at scale remained unresolved. But the evidence softened some of the hardest objections. The debate shifted from whether it was desirable to whether it was affordable. That is where the robot tax enters the picture. The logic is straightforward, even if the implementation is not. If a company replaces a worker with a machine, it stops paying payroll taxes on that worker's wages. The government loses revenue. The social safety net loses funding precisely at the moment when more people may need it. A tax on automated labor, structured in various ways, some targeting the machines themselves, some targeting the productivity gains they generate, could theoretically recapture some of that revenue and redirect it toward displaced workers or toward funding a basic income floor. Bill Gates floated a version of this idea publicly in 2017. South Korea enacted a modest version of it around the same time, reducing tax breaks for companies investing in automation. The European Parliament considered and then rejected a robot tax proposal. The debate has continued, unevenly, across different countries and different political traditions. It is genuinely hard to design well. Tax a robot too aggressively, and you slow adoption of technology that could genuinely improve lives. Tax it too lightly, and you accelerate a concentration of wealth that corrodes the social fabric. The calibration problem is real. What makes 2024 a particularly charged moment in this debate is the sheer pace of change. Generative artificial intelligence has entered the workforce in ways that extend automation far beyond physical labor and into cognitive tasks, writing, analysis, customer service, legal research, medical imaging. The economic recalculation is no longer confined to factory floors. It is happening in offices, in hospitals, in law firms, in newsrooms. The population of workers who might once have felt safely distant from automation is shrinking, and the policy apparatus for responding to this has not kept pace. Corporate profits in sectors with high automation intensity have, in many cases, reached historic highs. The gap between the earnings of companies at the technological frontier and those that are not has widened. Within companies, the gap between the compensation of workers who manage and design automated systems and those who are displaced by them has widened further. These are not abstract trends. They show up in the data on wealth concentration, on wage stagnation for median workers, on the geographic divergence between cities that are thriving and regions that are hollowing out. None of this is inevitable in the sense of being beyond human choice. Economies are not natural phenomena. They are systems built on rules, rules about property, about taxation, about what kinds of work get compensated and how. Those rules can be changed. They have been changed before, in response to earlier technological upheavals, when societies decided that the gains from industrialization should be more broadly shared. The 8-hour workday was not handed down from nature. Neither was the minimum wage, or Social Security, or any of the other structures that turned the productivity gains of the 20th century into broadly rising living standards. The question now is whether the political will exists to make analogous choices in time to matter, and that question is being answered, or not answered, by legislatures and regulatory bodies and corporate boardrooms and ballot boxes. Right now, while the machines keep running and the gains keep accumulating, and the distance between those at the top of the new economy and those at the bottom keeps growing. The recalculation is already underway. The only open question is who gets to do the math. And so the math is being done, whether we participate in it or not. That is perhaps the most important thing to understand as we arrive at this moment together. The calculation does not wait for consensus. It does not pause while we catch our breath. It runs continuously, in data centers and boardrooms and policy offices, and the results are being written into contracts and code and law faster than most people realize. But here is what is different about right now. Here is why 2024 is not simply another year in a long procession of years in which someone, somewhere, declared that this time the machines would change everything. The difference is that the change is no longer theoretical. It is no longer a projection on a slide deck or a thought experiment in an academic paper. The displacement is documented. The productivity gains are measured. The concentration of wealth is visible in the numbers. We are not standing at the edge of a transformation that might happen. We are standing inside one that already has. Every previous wave of automation reshaped certain categories of work, and eventually, after years of disruption and dislocation, new categories emerged to absorb the labor that had been pushed out. The loom displaced the handweaver, and factories grew up around the loom, and the handweaver's grandchildren found work that their grandparents could not have imagined. That story has been told so many times it has become almost a reflex. Someone raises a concern, and someone else invokes the loom. And for a very long time, the pattern held. What is different now is the scope of the target. Previous automation was largely confined to tasks that were physical, repetitive, and bounded. The machines were extraordinary at doing the same thing 10,000 times with perfect consistency. They were helpless in the face of ambiguity, context, and language. That boundary has moved. It has moved dramatically, and it has moved fast, and it has not stopped moving. The systems we are building now can draft a legal brief, compose a marketing campaign, write functional code, and synthesize a medical research summary. They are moving into the cognitive middle of the economy, not just the physical edges, and the cognitive middle is where an enormous portion of the educated workforce has lived for the past 50 years. This does not mean that the loom story is entirely wrong. New categories of work will emerge. Some are already emerging. But the pace of displacement and the pace of creation are not guaranteed to match each other. And the people who are displaced are not automatically the people who will be trained for what comes next. That gap between who loses and who gains is where the real policy challenge lives. So why does this particular moment matter? Why is this the window that the title of this chapter is pointing at? Because decisions made in the next few years will set the shape of the next few decades. The infrastructure of the new economy is being built right now. The legal frameworks are being written or left unwritten right now. The labor agreements, the tax structures, the educational curricula, the safety nets, all of it is either being redesigned for this new world or being left in place from the old one. And once the infrastructure solidifies, once the habits and the incentives and the institutions calcify around a particular arrangement, change becomes exponentially harder. We have seen this before, not with artificial intelligence, but with other moments of foundational choice. The decisions made in the post-war decades about housing policy and highway investment shaped American cities in ways that are still being argued over and still being paid for. The decisions made in the 1980s about financial regulation set the conditions for crises that arrived a generation later. Choices made at inflection points have very long shadows. That is what makes them inflection points. The question for societies, then, is whether they will treat this moment as a genuine emergency of democratic governance, or whether they will treat it as a technical matter to be sorted out by the people who built the technology. Those are two very different approaches, and they lead to two very different futures. One future looks like a negotiated transition, imperfect and contested, but broadly shared. The other looks like an optimization problem solved by a very small number of people in favor of a very small number of outcomes. The question for companies is whether they will choose to be architects of the broader transition or simply beneficiaries of it. This is not naive idealism. There are real business reasons to invest in workforce transition, to engage honestly with regulators, to think beyond the next quarter. Companies that extract maximum value from a disrupted workforce in the short term have historically not fared well when the social contract they depended on finally breaks. The infrastructure of trust in institutions, in markets, in the hegemony of the economic system itself is not free, and it is not inexhaustible. And the question for individuals is harder and more personal. It is about what skills to cultivate, yes, but it is also about how to participate in the decisions that will shape this transition. The most important choices ahead will not be made by algorithms. They will be made by people in legislatures and union halls and school board meetings and shareholder votes. The people who show up, who understand what is at stake, who refuse to treat this as someone else's problem. Those people will have a disproportionate influence on where this lands. None of this is destiny. That is the point. The future of work in an age of intelligent machines is not written, it is being written. The fact that we are inside the transformation does not mean we have lost the ability to shape it. History is full of moments when a disruptive force seemed to make certain outcomes inevitable, and then the outcomes turned out to be the result of choices that people made under pressure in the middle of the storm. The storm is the condition. The choices are still ours. What we owe to this moment is clarity. Clarity about what is actually happening, not what we hope is happening or fear is happening, but what the evidence shows. Clarity about who is bearing the costs and who is capturing the gains. Clarity about what we value and what we are willing to do to protect it. And then, after the clarity, the harder thing, the willingness to act on it, even when the action is inconvenient, even when the window is narrow, even when the machines keep running and the clock keeps moving, and the ground beneath us will not hold still. The ground has never held still. That has always been the condition of being human in a changing world. What we build on it, and for whom, is the only question that has ever really mattered.